3, 1, 2, 3. I hope I'm alive. Let's just check me. It seems I am. Okay. So hello everyone. As always, it is the Wednesday evening, so it's the high time we learned something about GC internals. Today we will cover topic of generations. So hello, and again, as always, I'm asking you say from where you are, so it will be very nice for me to see that someone is watching me at least and from where, for example, whether it is a morning, evening, or maybe even a night in your place. And without further ado, let's just also give me a kind of confirmation that you hear me well, because I'm always afraid that something is again misconfigured. So if you hear me okay, just give kind of confirmation on chat that it's okay, and I will try to give a talk assuming it is. So today we are covering generations. As you see, we are slowly ending the whole series, and the generations topic is super important. I must admit that I see this today's episode as one of the most important, because it covers the whole, one of maybe the most important concept in the whole .NET GC, which is the generation concept. So without understanding generations, all that we have covered so far could be applied, but it would not be, in case of .NET, something that is, gives you a whole picture how it all works. So okay, generations are super important. that's the message I would like to give you now, and let's just continue. So why generations? There was even such a question before in one of the episodes, why we have generations, why the concept of generations has been introduced. And this is all about partitioning, because as we covered all the episodes previously, all those things like marking, compacting, and all sweeping, all this could be done without partitioning, so it could be done for the whole managed heap. But the whole managed heap may be huge, so it wouldn't make much sense to consider whole managed heap every time we want to garbage collect something. And that's why we split somehow the managed heap into smaller pieces, we partition it somehow, which gives us this possibility that then we will be able to consider this or that partition, not the whole managed heap at the same time. And this partitioning may be done with respect to various attributes of objects typically, although we can imagine another partitioning schema, but typically we refer here to some object attributes. So for example, we can partition with respect to the size of an object. So we can have a place for big objects or small objects, whatever it means, whatever a threshold is. We can say, okay, this will be the threshold, and if the object is bigger, it will be created there. If it is smaller, it will be created there. We can also think about partitioning due to the type of the object. So imagine we have a separate space for strings or numbers, whatever. Then mutability. We could imagine that we have a smart runtime that treats somehow objects that are mutable differently from those which are immutable. We can imagine something like that. Or the lifetime. For example, the younger object may be treated differently than the object that is living for a long time. So the lifetime would be another kind of partitioning. And all these attributes are considered when we design the GC. In general, in any GC, in any managed environment, we are considering, regarding partitioning, those attributes. And in case of .NET, few of them were decided to be used. So first of all, we have the size. We partition it due to the size of an object. We have a small object heap and we have large object heap. Mostly here what are the benefits to consider objects due to the size? First of all, copying cost, because if we would like to compact a given partition, we expect that maybe compacting large objects will be much more costly because they are big, so copying them will introduce a big memory traffic. So we say, okay, so probably we will be a little bit more afraid of copying big objects. On the other hand, there is a different quantities that we expect. We could say from our everyday experience that we mostly create small objects, so we will be having many small objects which are often allocated. Most of our code is constantly allocating small objects, like small classes with only few fields. This is a typical object that we allocate, and because of that, because of this different quantity, it is wise to have them as a separate place, and we call this place small object heap. So we will be having small object heap for every object that is smaller than a given threshold. Then we have large object heap for everything which is bigger, and this is beneficial also because first of all we know that the big objects are there, so probably we will be not compacting them so often because we will be afraid of moving them in terms of the overhead. Also, we know that we rarely allocate them, so maybe we can not be so concerned about the allocation speed of them because we expect not so many objects being allocated there. Quite opposite in small object heap, you expect that constantly we allocate something there, so allocators there should be super fast. So this is beneficial for sure. Then we have another attribute that is recently used, like the type or kind of an object. In .NET 5, so very recently, there was a new addition. We have a pinned object heap, and this is a separate space, separate part of the managed heap, which is for pinned objects. So now with respect of the type also, we have a separate space in particular for objects that are pinned. So if an object is allocated as a pinned object, it will be moved there, which obviously means the new API has been introduced because we didn't have an API for allocating object and pinning it at the same time. So now we have no API for that. So pinning would be the one of this. And then we have those small object heap, large object heap, and pinned object heap. First of all, here we, as I said, many small objects are often allocated in small object heap. So SOH is the one that is mostly used. And I would say 99% of objects is living in a small object heap. So if we can say almost every object is living in small object heap, this partitioning is not super beneficial at that point because most of these objects would be living in this huge small object heap containing many small objects. So because of that, it is sensible to split small object heap even further, and then we will use the lifetime attribute, the very popular one in the GC design, the lifetime of an object. And the lifetime of an object is beneficial because it has been discovered, we can say, that two hypotheses are valid. They are called weak and strong generational hypotheses, and they sounds wise and they can be perceived as wise, but they are also aligned with our probably everyday experience. So those two hypotheses in general says that we have mostly two most distinctive type of objects in terms of lifetime. We have a large number of objects that are dying young, and we have pretty big number of objects that are living long. In other words, those hypotheses are saying that if an object is young, it will probably die young, and if an object is old, it probably will be living even more and to be living even longer because it is already old. So this splits our objects that we are having in a regular typical application into two groups: a large number of young objects and also a distinctive considerable amount of objects that are long living. And because of that, we will be splitting those all objects regarding to the lifetime, and we will split them into the young and old objects. And we can treat them differently, because if we expect that most objects are dying young, collecting and looking at objects in the young generation is wise to make it often, because we expect a lot of objects who should die there. On the other hand, if we know that some objects are gathering in the old generation, okay, that's nice, and we know that if they are old, they will be living even longer, so we can safely look at old generations rarely, less often, because we expect objects are not dying there often, and if they are dying there, if they are there, probably they should be there, and they will not die there in a short amount of time. So this is how it is organized, and all this is a design of so-called generational GC, and many popular GCs on the market, not only in the .NET but in general, are generational. So they split part of the managed heap into generations, and we have in .NET those generations, and as I introduced the whole story before, only small object heap is split into generations, because we expect most of the objects will be there, so we split only small object heap into the generations. And in case of .NET, we have three generations: young generation, old generation, and kind of temporary generations in between, and they are called 0, 1, and 2. Names are different, like in JVM there is, for example, simple young and old generation in one of the GCs. Here we have numbers: Gen 0, Gen 1, and Gen 2. So in the end, I hope you feel at least a little the rationale about the splitting all these things into smaller pieces, and in the end we have this logical organization of small object heap being split into generations, then large object heap, and recently pinned object heap only in .NET 5 and younger runtimes. So just a kind of summary to give you an overall grasp of what's going on. Object allocations happens in Gen 0 and in large object heap depending on the size, or in pinned object heap recently. So we can assume that most allocations happen in Gen 0, because this is the design that makes sense, because we expect if an object will be created, it will be not living long, it will be short living. It should be created at Gen 0, which is often collected, and then this object will be very fastly collected. So object allocations happens in Gen 0. And then there is this decision taken by the .NET team, and this is pretty wise decision, as we will see later on, that the GC will now be able to collect only part of the managed heap, but with this rule that if the GC collects a given generation, it will be also collecting all younger generations. So in the end, we have three possible types of GCs regarding the generations in .NET. We can have Gen 0 GC, and Gen 0 GC is just the one that is collecting Gen 0, as the name states. So if we are running Gen 0 GC, it simply means, okay, we are only considering objects in Gen 0. And it means a lot of objects should die there, because it is the young generation, and due to those hypotheses, most of the objects are dying young, so most of the objects should die there. And this is pretty fast at GC, because it is considering only single generation. GC also tracks and tries to not grow this generation too big, so it will be fast because it will not gather a lot of objects. On the other hand, it will be pretty often called because we expect it should be often called, and this additionally helps to make it fast, because if it is called often, it doesn't have a lot of work to do because it is collecting objects often, so there is not a lot of allocations in between. Then we have Gen1 GC, which is collecting both generations 0 and 1 with this with respect of this rule that we collect also all younger generations. If we see that we have Gen 1 GC, it doesn't mean that we have considered only Gen 1, but it means we have considered both Gen 0 and 1, and we have collected objects from Gen 0 and 1. And the last one could be called Gen 2 GC, but it is not, because of the reason that I will just probably you see it on the slide. Gen 2 GC is collecting objects from Gen 0, Gen 1 and Gen 2, so from all generations. But additionally, the decision has been taken that it is also considering large object heap and pinned object heap. So we can say that large and pinned object heap are treated as kind of Gen 2 logically. And because of that, it is called full GC, because as we see, it is just collecting everything, every generation in small object heap, large object heap, pinned object heap. So we can feel that full GC is much more costly, because obviously it needs to garbage collect everything in the end, while Gen 0 and Gen 1 GCs are pretty fast because they are limited in those generations that are considering, and GC is also concerned about not growing those generations too big to have those generation GCs being fast. So yes, this is the rule that is important for you to understand. This is a pretty basic thing, probably, maybe if you are expecting meaty things, stay tuned, we will have even assembler today, but this is something that it should be really described at this moment to have everyone on the same page. This is how we have 3 possible GCs in .NET. And as always, I forget to ask you that you can always, not to ask you, but to say that you can always ask questions, so do not hesitate to interrupt me, ask questions. I love questions because they show typically things from a little different point of view. So I'm trying to explain something, but your questions are always nice and they allow me to make things even more clear. At least I will try. So do not hesitate to ask questions, in other words. Okay, so we have this 3 possible GCs available, and then we have this important promotion idea, a promotion concept. So if an object, if we consider Gen 0 GC, for example, and if an object in Gen 0 will survive, we say that it will be promoted to Gen 1. If an object survives a generation GC, it will be promoted to the older GC. So objects from Gen 0 will be promoted to Gen 1, objects from Gen 1 will be promoted to Gen 2. Gen 2 will not be promoted to Gen 3 because we don't have Gen 3. Gen 2 objects will simply stay in generation 2 after full GC. And the same for large object heap. Large object heap also doesn't have any place to be promoted to, so a large object heap, which objects from large object heap that are surviving stay in large object heap. But this promotion concept is super important because it is the whole idea of this generational GC. If an object survives Gen 0, it probably means that it is not the one that will be short-living. So it is not this one of the hypotheses that, okay, this is short-living object, it will die soon, because it survived Gen 0 GC. So we are promoting into this temporary Gen 1 GC. And if later on we will be having GC that touches and considers generation 1 also, and it will also survive it, then it will be promoted to generation 2. And it will be staying there forever if it will be alive. So this promotion is an important concept because it tries to be aligned with those hypotheses. We are promoting here only after single survivor of the GC. There are GCs, for example, in Java when there is a threshold. So, for example, object needs to survive some given amount of times, and only then we are promoting it to the older generation. Here we have this threshold set to 1. So only single survival of the GC will promote it to the older generation, sorry. And what's important from this perspective is that you should always remember that the only full GC considers all objects on the managed heap. But for example, Gen 1 GC considers only objects in generations 0 and 1. So from this perspective, we should say that, in other words, when a generation isn't collected, we can simply treat all objects in that generation as live, because we are not considering it. So in Gen 1 GC, for example, we are collecting objects from Gen 0 and 1, but we don't look at Gen 2. And during Gen 1 GC, we simply treat all objects in Gen 2 as live. Pretty maybe clear thing, but it is worth pointing out that it is something that happens, that we are not all the time considering all the generations. So let's say that we have this scenario that you see that you have a lot of Gen 2 objects in your managed heap because you have taken a memory dump, and it doesn't mean, looking at this description, that all objects are there really alive, but it may mean that there were no full GCs, we haven't considered the Gen 2, and we are simply treating all objects in Gen 2 as alive because we just haven't collected Gen 2 yet. So we are treating all those objects as alive because we don't have anything else to do. Okay, and generations are considered in various places. So if you add generation concept to the GC, out of a sudden these generations will be just happening everywhere else. So for example, if you have a finalization queue now, which tracks objects that are having finalizers, now it needs to be generational. It needs to be considering generations. So we will not be scanning the whole finalization queue, but only the part of the finalization queue which is covering the generations that we are collecting in this particular GC. And only other places may happen to be generational because we have now just introduced the generation concept and we have split small object heap into those 3 generations. I hope it is clear. Just give me a kind of, if there are any questions, I assume at least someone gets a little understanding of it. Okay, so then having said that we have those small object heap, large object heap, and pinned object heap, I would say, okay, I see one question, and fortunately I need to use this very unfortunate way of showing it, which is just showing StreamYard for a moment. So you said that you are finalization queue is not considered only during the full GC, but it is finalization queue is treated as a kind of route, an additional route, and it needs to be treated as a every time. So there may be objects in Gen 0, Gen 1, Gen 2, that are lying in the finalization queue, and then we need to consider them with respect to the generations, right? So it was not a question, but kind of confirmation. Is possible to have is Gen 2 possible without large object heap and small object heap? No. Currently there is not such a mode of the GC working, that it is only, for example, considering Gen 2, we are always having all on the same time. So we cannot, for example, garbage collect only large object heap or only Gen 2. Which is one of the reasons why we should be, for example, really careful about allocating things in large object heap, because if you allocate a lot in large object heap, you will start triggering full GC, which will trigger all the managed heap collection, including all the Gen 2 objects. So be careful, simply. Okay. So having said that, let's look at the physical organization a little, because it is also pretty interesting. And here we have a concept of segment. So we have something that we are reserving. We can call it block, although this name is not official, and there you will not meet it in a source code of the GC, for example. We reserve a huge amount of memory, which I'm calling block, and then you split it into two segments. You reserve, this reserved space is for small object heap and for large object heap. Reservation is mostly important on Windows because it has this two-phase way of committing memory. So at the very first phase we are reserving a huge amount of memory, and it is kind of reservation for our process, a reservation of virtual address space, but it does not consume this memory physically. So this may be in terabytes even, and we don't care because we are just have reserved 1 terabyte of virtual address space. And then we logically split this reserved space into those two segments, and only then we commit some part of it at the very beginning. Pretty small part because we don't have any objects yet allocated, so we will be committing some pages inside large object heap and small object heap. And due to what I was saying, the committed part in the small object heap segment will be also splitted into generations. Large object heap is not. And this is how it is physically organized. We have those two segments lying next to each other typically, as you will see, not always, as you will soon see, it is not always the true, but typically they are laid next to each other. And obviously while we allocate, we will commit more and more memory up to the reserved amount of memory in, for example, small object heap segment, and we will see what will happen because I will also describe that. But the committing is the part of the, I've even covered that during the allocation episode when I described that when there is no place for a current, when the current allocation context is filled, we are looking for a place for a new allocation context, and this may triggering some pages from the reserve, committing some pages from the reserved pages to have a place for a new allocation context. Okay, so this is a physical organization, and if you look at the managed, at the memory of the .NET application, for example, with the help of VM map tool, which is pretty nice and free tool that allows you to see virtual memory of a process, VM map tool, then you will see that the managed heap is indeed splitted like I described. So you will see, for example, over almost 400 megabytes of memory, which is called managed heap, and then some memory will be for the generations. So we have here small object heap and also large object heap, from which only very small part is already committed, and most of it is only reserved, because this is the columns that we have here. It is the reserved column and committed column somewhere here. And you can ask, what are the sizes of those segments? Because here we are seeing the small object heap and here we are seeing large object heap. What are the sizes of those segments? And as you see here on the table, they really depend on various things. like the mode of the GC, the very first workstation and server GC influence the size of the segments. Also the bitness of the runtime influence the size of the segments. So I would say those two are most typically used currently. So in case of workstation, 64-bit applications, which are all Windows forms, all WPF applications and so on, the small object heap has this size and large object heap has this size. Not super big sizes, in fact, because as far as I remember, I was describing, the workstation tries to be a nice for the whole environment and do not consume too much memory. The different stories with the server, which assumes that a lot of memory might be consumed. So while this large object heap is again not so big because we don't expect it should have a lot of objects there, we can have a pretty big small object heap segments. Even 4 GB may be dedicated for a single small object heap segment, and this additionally depends on the number of logical CPU cores, as you see, because as you may remember, in case of server GC we have as many managed heaps as logical cores on the machine. This can be limited additionally, but in general by default we have as many managed heaps as logical cores on the CPU as on the logical cores on the machine. So for example, a pretty typical scenario, 8 logical cores, so my machine has 8 logical cores. Even many servers have 8 logical cores. It will have 2 GB for small object heap multiplied by the number of logical cores, so 16 GB for small object heap segments will be dedicated in case of server GC, which is aligned with this decision that in case of the server GC we would like to be pretty aggressive in memory consumption, because we assume we are server and we can consume memory because we are for that purpose using our application. And as you can see, as I said, those numbers are pretty small in case of workstation. What else? So physically they are organized as I described you, so we can have, typically we will be having small object heap and large object heap lying next to each other. If the GC won't be, maybe we can say, if the runtime won't be able to reserve enough continuous memory region, it will split it into 2 smaller memory regions and we will have separate small and large object heap. But this would be in the case of virtual memory fragmentation, which is rather not the case. In 64 environment, the virtual address space is so huge that without any problems the runtime should be able to reserve this memory region at once as a continuous memory region. And in workstation GC, as we see here, we have only single small object heap and single large object heap. In case of server GC, we have, as I said previously, as many heaps as logical cores. So here we have an illustration for the case when we have 4 logical cores on the machine, and which means we will be having 4 small object heaps and 4 large object heaps in one single continuous memory region. Typically runtime will be able to reserve such a huge amount of memory, and as you saw on the table, in case of 4 core machine, it means if we are in this scenario, every single small object heap will be 4 GB, so it will be 16 GB of small object heaps and 1 GB for large object heaps. 16 GB of memory reserved for the purpose of those segments. Only reserved gigabytes, not consumed. If the memory, if the virtual memory is fragmented, it will be trying to split those segments into smaller regions to fit within those fragmentation. So it will be just separate addresses, separate range of addresses for every segment, for example. But this is really not the case in the scenario when we are using 64-bit runtime. So this is how it is physically organized. And remember, inside small object heap we have also this generations concept being handled. The physical anatomy of single segment is pretty easy. We have a single page at the very beginning. It is a page, single page, so 4 kilobytes, to contain some segment information. So many data describing this, not so many in fact, but some data describing what's inside this segment is there. It is called segment info. Question for you: why do you think it is one page size dedicated only for that purpose? If you know, try to tell on the chat. And after this single page we have simple objects lying inside our committed space. So from within the all the reserved space we will be committing some memory, and we are committing in advance, so typically always there is kind of margin here for the committed memory not yet used for objects, because if we decide to commit from the operating system we will commit in some batches. So I don't remember the size of this batch, but we will commit some size because we expect if we are committing probably we will need more space, so let's just take it in advance with some margin. And objects inside the committed part. There is this pretty important allocated pointer also tracking where all those allocated currently living objects are ending. Where is the last place when the objects has been allocated, and for that we have this pointer. We have also begin pointer, called also mem sometimes inside the core CLR source code, which is just the beginning where the objects inside these segments are starting. Okay, and then this is about physical organization, and let's look at the generations concepts, because this is about generations, which needed some background in terms of these physical things that I've described, but we are about generations today, right? So generations, let's give me just a generation is, as I said, think about promoting things between, and those things are objects. So we could say, okay, so we have conceptually something like that, that there is, for example, here we have these buckets of generation 0, 1 and 2, and imagine that we have scenario at some point in time that we have so far allocated object A, B and C. Super nice. So they have been allocated in gen 0 as we said, and after some time we consider gen 0 GC, and we discovered that object A is no longer needed, so we promote object B and C to the generation 1, which could be seen as moving those objects into this bucket. After some time we will be allocating object D. After some time we will discover that B is no longer, here was A no longer needed. Here we, after some time, for example, could discover B is no longer reachable, and we promote C to generation 2, and we promote D to generation 1, and so on and so on. Conceptually, you can imagine that this promotions works like that. It is working objects between buckets, but it is not the case how it is implemented. So please, if you could remember at least one thing from this webinar today, it would be that it is not working like that. We are not copying objects to move them between generations. That would be super inefficient, and we would be really not happy if we would design that in that way. So I'm just describing this mostly because at least once I've met an article that was showing that it is implemented that way. At least it was misleading the reader that it works like that. It doesn't work like that. So how it does work? And I tweeted even today about this because it is pretty heart of the concept of generations that we are describing here at now. So generations are not buckets. We are not promoting objects between generations by copying anything, because it would be super inefficient. So we are doing it in totally opposite way. Instead of moving objects, we are moving generation boundaries. And we have here this scenario described. So generation simply is a boundary, a logical boundary that we can move. And here we have a pretty typical scenario of correct, so I can already say that it is working like that, you can remember that. So we have here this scenario described. Again, the same as previously, but now correctly visualized. So step number the first step, imagine that we have already allocated some objects A, B, C, and they are obviously inside the gen 0 because where we are allocating objects. After some time we made the GC, we discovered that A is no longer needed, so after the sweeping webinar we know that we can sweep this object by marking it as a free space, and then B and C should be promoted to gen 1. And we are doing this promotion simply by moving the boundary of the generation. So while it was starting here, after this GC, we will say, okay, so gen 0 starts here, and it means that the gen 1 is now from here to there. So it is now the boundary of gen 1. So as you see, we have promoted object B and C to our older generation, not by moving this object, but by moving the boundary of gen 0, and now the gen 1 has grown simply because it is now containing all those two objects. And this is how those generation boundaries are working. So here we have something like that. After some time we can allocate object D, and as we know from the allocation webinar, it is happening somewhere here in the allocation context. We can imagine this allocation context is at the very beginning of gen 0, so we have allocated in this object here. After some time we have discovered, okay, B is no longer needed, and again we promote those objects by moving boundary generations. So now we have just moved the boundary of gen 0 more, and again we have moved the boundary of generation 1. So simply now gen 2 is from here to here, and it means this is the generation 2. And as you see, logically it means that that object C has been promoted from gen 1 to 2, because now previously it was within the boundaries of gen 1, and now it is in the boundaries of generation 2. The same for the generation 1 and the object D. It was within the gen 0 generation. After moving the boundaries, now it is within the gen 1 generation, so it has been promoted from gen 0 to gen 1, and so on and so on. This how the story continues. So by moving those boundaries, we are simply promoting these objects between generations. And this is how those generations are handled. They are simply logical boundaries within the managed heap. And now we can use this information during our GC. One side note here, this generation 0 here is marked as a whole segment, but in the end it is not taking so much space, so logically we could say that generation 0 ends somewhere here, and this is the real generation 0. We have some space for generation 0, the rest is just kind of this committed space that will be used, but this is a small side note that doesn't change a lot in the understanding of all those things. Okay, so we have covered that we have generations and they have boundaries, logical boundaries. So let's just see how do we use those generations and those boundaries. So imagine we have this scenario. I prepared this, and this scenario that already we understand this. We have this here large object heap segment, we have small object heap segment here, and I assume that we have already some objects. So we have taken memory dump, and we see that we have some objects in Gen 2, we have 3 objects in Gen 2, we have 3 objects in Gen 1, and we have 4 objects in Gen 0. This is a snapshot of memory that we will be using in the next slides, from where we are starting. And now let's look how the GC will look for those particular possible generations that we can collect. So Gen 0 GC as the very first one. Gen 0 GC, as we said, considers only generation 0. And because we know the boundaries of generation 0, it means that we will be only interested in this memory region, because we perfectly know where is the generation 0. Which means all the phases will be that I described previously, the whole marking, sweeping, compacting, everything will be happening only inside this particular region, which is generation 0. So this is why I'm saying everything that I've covered so far is valid, with this addition that it is applied not typically for the whole managed heap, but it is applied for small part of the generation. Here we have this part, like for example generation 0. And the marking in particular will be happening only for this particular memory region. So when we have Gen 0 GC and we are interested only in Gen 0, we will be considering and scanning only objects inside this memory region. So for example, we can discover that, okay, only this one single object has survived. So this is how I mark it. Here I marking it as it has been marked after the mark phase, whether it was concurrent or not. In case of Gen 0 it was not, but I have marked this object as live, and it means now we can garbage collect Gen 0, and we have those two possibilities. We can sweep or we can compact. B is sweeping, C is compacting. So if we sweep, we will be not moving any objects, and it will be exactly the scenario that I've covered previously. We will be moving only generation boundaries, and we will be moving those boundaries in that way that objects that should be promoted will be promoted. So here we have this example. Because we want to promote this object, we need to set the boundary of the Gen 1 after this object. So now it means, okay, really this object has been promoted from generation 0 to generation 1. Generation 0 is empty, and this is pretty typical because we expect nothing should survive there, because if something has survived Gen 0, from Gen 0 should be promoted to Gen 1, so Gen 0 should be empty. It obviously sweeping introduce fragmentation here. So because we haven't moved any object, it means, okay, we very fastly moved the boundary of the generation. We have promoted what has been what has to be promoted, but we introduced fragmentation. On the other hand, sweeping will be much more optimal, so we will compact everything, we will move objects next to each other, but it will introduce some copy of objects, so bigger memory traffic. We know that the plan phase would be responsible for planning all this, and in the end we will have these generations boundaries also recalculated, because now this object has been moved obviously to another place, and accordingly to that we will set this boundary to here to promote this object, while Gen 0 should be empty again. I see some question. Let's just look at this question. So allocator So the question is whether the allocator allocates in gaps in Gen 0 and Gen 1. In this ideal scenario, we will be not allocating in Gen 0, but Gen 0 allocator is used for finding allocation contexts. So if you recall, and if you haven't watched, you should watch allocations webinar, and then before the GC is being triggered, we try to find the space for new allocation context, and it means we will use allocator for that. We will try to find a gap inside Gen 0 big enough to find to fit the new allocation context there. Moreover, this is an ideal scenario, but as you will see by the end of the presentation, pinning adds a lot of complexity here, and we can have gaps in Gen 0, and in general Gen 0 could not be empty because of pinning. So yes, there are some scenarios when the allocator can allocate in Gen 0, trying to find the gaps there. And with Gen 1 story, I will return to that soon. So I hope the answer for that will be clear just in a few minutes. So let's postpone answer for that for a second. Okay, so this is a Gen 0 GC, the pretty fast one. If the Gen 0 is not big, it will be pretty fast. As you see, you promoted things to Gen 1. Obviously, it means that when we are doing Gen 0, Gen 1 will grow. Obviously, Gen 1 will grow while we are doing Gen 0, because this is the purpose of it. We are promoting things from Gen 0 to Gen 1. In case of Gen 1 GC, the story is very similar, but we are simply starting from the boundary of the Gen 1. So not from the boundary of Gen 0, but now we are considering both generations. We are starting at the beginning of Gen 1 and going to the right. And this, as you see, it's pretty good from the perspective of all these algorithms that I described. So marking, traversing, scanning object by object, it doesn't matter, in fact, where, for example, is the generation boundary, because we are simply saying start from there and scan to the end. And from where we're starting, from there we are considering the generation 1, 2, or 0. So this line of objects and generations being next to each other from the old to young generation is helpful here, because we can start from here, and now to garbage collect everything, we need to simply scan from the beginning to the end. And now, because now we are in the Gen 1 GC, we are scanning Gen 1 and 0, so we will, for example, discover that those three objects are still reachable, and those should be garbage collected. So again, a decision whether to sweep or compact. If we will sweep, very similar scenario, without moving any objects, we will simply move the boundaries of the generations. And now we will move boundary of both generations, because the generation 2 needs to grow, because we have just promoted those two objects has been promoted to Gen 2, and the Gen 2 grows, and these objects should be promoted to Gen 1. So we need to move both boundaries, and now everything is as expected. This object has been promoted, those two objects has been promoted, and Gen 0 is empty. And again, fragmentation, so we are sad, because fragmentation has been introduced, but there are always some compromises to be decided. In case of compacting, obviously we are compacting every object next to each other, and we calculate good boundaries, new boundaries for generations. Always we don't look at large object heap and pinned object heap, because we are about Gen 0 and 1 GC. And this is a little more work to do, like twice more, because Gen 0 and Gen 1 can be it really depends, but we know Gen 1 is not so big typically, so the difference between the performance, for example, but between Gen 0 and Gen 1 is not so big, because they are pretty similar in what they have to do. And then we have the full GC, the one which is about collecting everything. And now we are doing the whole managed heap scan, including large object heap and the pinned object heap. So we start from the very beginning, and then we are moving to the end, scanning all objects, scanning large object heap, and collecting everything. And again, compacting or sweeping will be decided. Moving generation boundaries. Obviously, a lot of fragmentation may be introduced in this case, for example, but it may be pretty fast and maybe concurrently, while when we want to compact, we need to stop all the threads, because we don't have concurrent compacting GC currently in .NET. Again, Gen 0 should be empty, and all the generations boundaries has been properly moved to promote every object to the proper generation. And as you see, it is now repeating. So after this particular run of the full GC, the next GC, for example, the Gen 1 GC, would be interested only in this place, or this place in case of the scenario after compacting. If we would be interested in Gen 0, we will be considering only objects that has been allocated before it, and so on and so on. And because of these boundaries, we can pretty nicely track what we need to collect, and it reduces a lot of work, because you can imagine that this scenario, when you consider only Gen 0, requires a lot of less work, for example, in terms of marking, because we have only small subset of objects to be marked, to be traversed instead, and comparing it to the full GC, when we simply need to traverse the whole object graph on the managed heap. So a lot of references to be followed. And this is the heart of the GC and explaining it, what these generations are doing. One more thing, and now just to it will also answer your question regarding Gen 1 GC and allocation in gaps there. When we are compacting, we can make something magical, but also pretty let's say straightforward and beneficial at the same side and the same moment. That imagine that we have some gaps, and we are, for example, doing Gen 1 GC. So instead of just doing the things that I've described before, we can reuse some gaps in the older generations to move those objects to the gaps inside the older generation. So in this scenario, when we are doing Gen 1 GC, we have discovered that those three objects should be promoted and should survive. So we are compacting, so we are now in this possibility that we can move objects. So we can, for example, find a gap for an object A inside the older generation. So part of this free space will be used for object A, and it will be moved there, and then we are moving then object by object, simply one after another, and then obviously calculating the boundaries of generations. But this is the scenario when we use the allocate in the older generation routine, and I was saying about that when I was describing allocators, because exactly for that purpose we need allocators in the Gen 1 and 2. And Gen 1, for example, also maintains a free list of space, because when we are doing only Gen 0, then, and it is a compacting GC, we would like to find free space for objects that are promoted from Gen 0 to Gen 1. So then this allocator will be useful, and we will be able to find a gap in Gen 1 for an object promoted from Gen 0. And this is super nice way of fighting, or maybe a better word, reusing fragmentation in older generations. And this is obviously used for Gen 0 and 1 GCs, because when we Gen 2, we are simply compacting everything, so there is no older generation to allocate into. But in case of Gen 0 and Gen 1, this is how, in case of compacting GC, this is how we can reuse fragmentation. And this is pretty nice feature that is able to make use of this fragmentation instead of treating it as a unusable space. Okay, and then one more scenario, which is touching the physical organization of generations. At some point in time, we can run out of the small object heap segment, obviously, because if we allocate a lot of objects, and we can even need a lot of them, because obviously we need some objects, so keeping objects in memory is not a bad thing. We can just run out of the small object heap, like here. So we are just touch the whole segment, and all the committed memory has been consumed here, and even after the GC has been triggered and it calculated planning or sweeping, it may discover that it is just not fitting the small object heap, because we have just simply allocated so many objects. And in this scenario, we will simply create a new segment for that. So there will be a new segment created, and this will be committed and reserved again, similarly as previously. So we will create a new segment for it, and we will do the magic, because simply what does it mean? We will need to copy some objects, as you see here, because we have here some objects that has been promoted to Gen 2. So all those objects stay after compaction in the same segment, and those objects from Gen 1 also has been compacted inside this Gen 2 segment. And what to do with this object, which is Gen 0 and then should be promoted to Gen 1, and we simply don't want to have segment with Gen 2 and 1 inside, and we want to have a segment which will contain always generation 1 and 0. This is the decision. So instead we are just moving these objects to the new segment and gathering some objects promoted from Gen 0 to Gen 1 inside this new segment. And this is what is happening. So when we are running out of small object heap segment, we create a new one. This new one is called ephemeral segment. Sorry, not the new one. There is this ephemeral segment, which is the one which contains Gen 0 and 1. This is called ephemeral because we are often collecting this memory, because we are often collecting Gen 1 or 0. It is nice to have it separated, and this is called ephemeral segment. So after some time, we will be having ephemeral segment and at least one Gen 2 only segment. We can call it Gen 2 segment simply, which will contain this object, and one ephemeral segment. Okay, I see some questions on the chat, so let's skip to the StreamYard magical tool, and let's look. Yes, so first of all, you can say new objects are never allocated in Gen 1 and Gen 2. So your code will never allocate new object in Gen 1 or 2. If you new up object in C#, for example, it is by design allocated in Gen 0, or large object heap if it is big, or pinned object heap if it is pinned. But recently there is this new API called gc.allocate uninitialized array, And one of its possibilities is to give you an array which is not zeroed, which is not cleared, which means we don't need allocation context for allocating this object. So as a kind of implementation detail, GC is free now to use one of the free space in Gen 1 or 2 to give you this space for this array, because we don't have allocation context, we don't need to zero this memory, so we could think about using free space from older generation. But this is kind of implementation detail. We can stay with this knowledge that typically our code will just be allocated in Gen 0 or large object heap. Does the ranges of Gen 0 and Gen 1 move back? Yes, they can move back. It was even this scenario showed. So in case of full GC, here we have that this boundaries has been moved back. In case of compacting, because not so many objects has survived, so the generations boundaries has been moved back. I hope it was with the question. Okay, another questions. Can Gen 2 be compacted? Yes. This was the case. Gen 2 GC, full GC, and the C is scenario is when we compact the Gen 2, because it is what we are doing here in the end. We started with this scenario and we have compacted all generations, because if we decide to compact, we compact all generations that are considered in the particular GC. So if we are doing Gen 2 GC, also known as full GC, and it is compacting, we are compacting all generations. If we are doing Gen 1 GC, which is compacting, we will compact Gen 1 and 0, and so on and so on. Okay, let's just check me if I have skipped. Okay, and the next question is how does GC deals with the fragmentation of large object heap if it never gets compacted? How to answer that question politically? It doesn't deal with that. Like, for many years the large object heap was never compacted, so it was one of the implementation details that you could kick your back, because you could introduce huge fragmentation in large object heap, and you should then be aware of that and introduce your own solution and solutions and workarounds in code, like for example reuse objects in large object heap instead of creating them all the time. Recently, and because of that, many years ago, there is also this flag that you can trigger manually in code compaction of large object heap. So for people that were having problems because of fragmentation of large object heap, they could also use this workaround to manually trigger the compacting of large object heap, but that was kind of a workaround for sure. And only recently in the container scenarios, the GC for the very first time, and as far as know it is since .NET 5, in the container scenarios, when you are setting the limits of the managed heap, so the GC is aware that it is working in a kind of limited scenario. For the very first time, the large object heap will be compacted automatically in these scenarios. So yes, sometimes it will. Now we'll try to handle this simply by compacting large object heap, but not in every scenario. So you should be really aware of that problem. Okay. No more questions at that point. I hope I've answered your questions. So let's just move, because it is not the end, and today's webinar will be longer for sure, because this is the pretty a lot of topics, important topics that I didn't want to split into two separate webinars. So Let's just continue. Then we have a Gen1 segment created here, and obviously the story may continue and repeat. So after some time, this Gen2 segment may be filled with data, which will be still alive. So we will then need to create a new Gen2 segments, and in the end we can have multiple Gen2 segments. And then all the time we will have this decision how to create a new ephemeral segment. Typically we will just create a new one. Sometimes we will be able to reuse a segment that is from the standby list, because if in one of the previous GCs one of the segments has been emptied totally, so it was an empty segment, instead of just returning it to the operating system, we can put it in on so-called standby list, and this is what can be then reused when we need a new segment. We can reuse a segment from this list. And additionally, there is this optimization that is in the GC, that if there is a imagine that we need a new ephemeral segment, and there is also a Gen2 segment, but it does not contain a lot of data. Like here we have it. There is such a segment that doesn't contain a lot of data. So instead of committing and creating a new segment, GC will be able to do some magic and create a new ephemeral segment from this segment, and just leaving some part of Gen2 in this segment from the old one. And that's nice, because it is all about reusing committed memory instead of committing more and more memory, which is always thing that in the end counts as a memory consumption of our process. But this is a kind of implementation detail. I will not stay here for a long time. And before moving to this super important allocation object, allocation budget concept, I see a question. So GC will never compact large object heap in older versions, but it can choose to compact Gen 0. So can we say that when the compaction was chosen in planning phase? No. In case of the compacting full GC, in the normal scenario, the large object heap will be simply swept. So it will be something that generations are compacted, but large object heap is simply using sweeping. Okay, drink. Allocation budget. This is super important concept again regarding generations. So as you already seen, objects are allocated in Gen 0 or large object heap by our code, or allocated by promotion from generation 0 or 1 into older generations. So in other words, generations are growing, and because objects are being allocated in all of those generations, Gen 0 and large object heap because of our code, Gen 1 and 2 because of promotion. And in other words, generations may grow in time, and probably will, so they can exceed something that is called allocation budget. Allocation budget is something that we keep for every generation. So GC tracks consumption of allocation budgets per generation and uses this to decide what generation should be collected, and for that we have this condemned word used, very popular word in the GC source code and the terminology. So we have the condemned generation. So the allocation budget will be one of the main reasons to decide which generation should be condemned. So typical flow is like that, because you always hear in the talks and books and everywhere that you can have a Gen 2 or Gen 1 or Gen 0 GC. But how it happens that, for example, the GC decides to make a full GC. So the typical flow is like that. We allocate an object, and because we new upped something in the code, and then the GC is not triggered, but first of all, the execution engine runtime, the GC, tries to find a imagine that we are running out of the allocation context. It has been filled, and this has been covered in the previous webinar. So we need to find a space for a new allocation context. And imagine we can't find this space. So we cannot, for example, commit more memory because we are running out of the reserved memory, or so. So we cannot find a space for a new allocation context. So now the GC is really triggered. And initially we can say it is always initially triggered for Gen 0 because it was the allocation in Gen 0 that has been the reason why we are doing the GC. So initially the Gen 0 is condemned, like we could say that. But then before doing the Gen 0 GC, the GC will look around and try to decide on the condemned generation. This is the exact name of the method in the code doing this. And it is simply selecting which generations should be condemned. And looking at the allocation context will be the most typical reasons to increase this generation. So why we started because of the allocation, so because of running out of the allocation context, initially it will be Gen 0, but at this point in time the GC may see that, okay, but because of the previous GCs we have exceeded the allocation budget, for example, for generation 1. And it means, okay, so because generation 1 allocation budget has been exceeded, we need to bump the condemned generation to the generation 1, or 2 if the generation 2 allocation budget has been exceeded. This is the most typical reason why we are increasing the condemned generation. Also, there may be other reasons, right? Running out of ephemeral segment and all the other reasons, but allocation budget takes a very important role here. And if you, for example, would be using purview and there is this GC stats table, you will see reasons for the condemned generations for every GC, and there you will see what was the decision for the particular GC, which generation should be condemned and why, and allocation budget will be the one of the column that will be typically deciding what the GC decided as a condemned generation. So as you see, allocation budget is pretty important thing. I would say allocation budget is the heart of the whole heuristics in the GC, trying to decide what should be collected, simply which generation should be collected. So if you would like to hear kind of definition, allocation budget is a total size that the GC would like to spend on allocations in a particular generation. So it is saying like, okay, Gen 0 should not allocate more than 1 gigabyte or 1 to 100 megabytes, for example. Or Gen 1 should not allocate more than 200 megabytes. So this is the total size of objects that should be allocated inside the particular generation. This doesn't make maybe a lot of magical, but things are getting complex if we realize that the allocation budget is changed dynamically. On every GC that collects a particular generation, we recalculate the allocation budget for this generation. So this is kind of dynamically changed all the time. Our will to allocate a given number of bytes in every generation. And then there is a minimum and maximum of this allocation budget set for every generation, so it will not exceed those two values. And if we would look at the code, mostly the new allocation budget for a generation is based on the survival rate. This is a super important thing and information for the GC. The survival rate is the ratio of the size of object that survived with respect to the total size of the given generation. So in general, it can be seen as a percent of size of relational size of object that survive the GC in a particular generation. And the survival rate is so super important driver because it is something that is trying to fine-tune to this hypothesis that I described about being objects or short-living or long-living. So for example, if the survival rate of a given generation is high, it means a lot of object has survived a given generation, which means a lot of those objects, so a lot of memory has been promoted to an older generation. The GC will increase the allocation budget because we don't want to promote prematurely. Probably the allocation budget is too low and we have promoted too many objects because we would rather expect that most objects should die and not be promoted. So we simply, by increasing the allocation budget, we count on a better ratio of dead to live objects into the next GC. On the other hand, if the survival rate is small, we are doing the opposite to the above, because this is what we would expect. And also we would like to keep generations small in general because it makes sense, because we would like to have less work to do. So smaller generation means less work to do. So the generation should be as small as possible. So by the survival rate, which is calculated after every GC, we recalculate the allocation budget. And additionally, there is the fine-tuning how dynamically the generation allocation budget changes, and we can say that the younger generation, the more dynamic changes. So for example, why the generation 2 is not so super willing to increase or decrease the allocation budget with the respect to the survival rate, Gen 0 is changing it as a crazy because it is just treating it as a super dynamic thing, so it will be much more willing to change this allocation budget. And if you ever will hear about that the GC in .NET has some heuristics that tries to make this GC optimal, this will be one of those. I would say the most, maybe even the most important heuristic. Try to calculate allocation budgets in a way that they will be aligned with the proper survival rates, so it will be really generational, so it will be really aligned with those generational hypotheses. And this is even a graph that shows you how the new allocation budget will be calculated based on the survival rate. This graph is really changing depending on some fine-tuned parameters for every generation, but the whole concept is like you see here. Based on the survival rate, whether nothing has survived or maybe everything has survived, we will be just setting the allocation budget somewhere from between the minimum generation size and maximum generation size, which by generation size I would rather say to here probably minimum and maximum allocation budget. So as you see, the concept of generation size is pretty complex, because in the end generation size is just a kind of the current dynamic result of the applying the dynamic allocation budget. So the generation size will be slow, but will be simply following and be aligned to the allocation budget that is decided on the survival rate. So the answer, for example, what is the maximum size of the generation 1 or 2 is not so easy, because it is super dynamic, as you see here. It is based on this survival rate, which is then driving the allocation budget. And this minimum and maximum is per generation static data, and also the survival rate and how dynamic is the reaction is also part of the dynamic data, and this static data, sorry. And this static data is presented here, just a kind of example for you to see what are the sizes, what are the values considered here. So here we have the static data for so-called balanced mode, which is the typical mode in which we can run the GC, one of the modes with which we can run the GC. And as you see, those two columns are the one that we are interested here, the minimum and maximum allocation budget. And it is for every generation. And additionally, we have point object here, which is very similar to large object here, but those three are most important because those three are most dynamic. So minimum allocation budget and maximum allocation budget may be seen as this minimum and maximum generation size between which this generation size will be flowing depending on the survival rate and the current allocation budget. So the allocation budget will be within those values. And they are calculated based on, for example, the CPU cache size. And those values are for the scenario when we have 8 megabyte of the cache size. So they are calculated mostly on the cache size of the CPU that we are currently executing on. And there are even special conditions for specific vendors to make some fine tunings. What should be the size of those generation budgets? And because this is the one of the most important generation that should be big enough to not promote too many objects, but not too big enough to don't have to a lot of work, those two parameters are pretty important. And then we have the same for Gen 1 and 2. As you see, the maximum size of Gen 2 is infinite because it can in fact gather all the memory in the process. Most typical things are happening here. What are the minimum maximum values for those two ephemeral generations? Additionally, we have those two parameters which are simply parameters provided to this graph. So when we calculate this graph that I presented in a previous slide, this graph has more or less step of the curve depending on the parameters. The higher parameters, the more dynamic reaction to the allocation budget, to the survival rate. So as you see, it is all calculated on the basics of some parameters provided there. Those are pretty deep things, like I've checked even, and those values hasn't been changed since my book publication, but may be changed in the future because maybe the GC team will decide we need to change some values here or there. So in the end, you can see the generation size as something that is dynamically following the allocation budget, which is based on the survival rate of the particular generations. Pretty dynamic thing regarding how the sizes of generations are calculated. Okay, so moving further, we have two topics. I expect at least 10 minutes that will take to describe them. Again, remember to ask questions if you have any. So at this point, you should understand, at least in overall, how those generations are organized. We have two more topics. The very first is card tables. So imagine that during the GC, and you don't have to imagine, like it is the fact that during the GC mark phase, we consider only condemned and younger generations. So if we have a Gen 1 GC, it means that we will be marking objects in Gen 0 and 1 only. We will not look at any Gen 2 objects. We will not look at Gen 2 at all because it is Gen 1 generation GC. So imagine that we have, for example, Gen 0 in a scenario presented here. So we are doing Gen 0, and here objects are just flying around because I don't want to provide here more physical layout, but conceptually we can imagine that we have this generation 0 and then we have generation 1. And because we are doing Gen 0, it means that we will be considering only generation 0, right? And because of that, because we are considering only generation 0, imagine how the mark phase will be looking here. It was covered in the previous episodes, but it will be very fast to follow. We are starting from the roots, so we start from this root, and because of marking, we mark this object as reachable, and we follow this reference, so we mark this object as reachable, and that's end. We don't have any more outgoing references to follow. So we go to the next root, like local variable. We start from it and we try to go to this reference, but as we see, it is in Gen 1, so we are not following it at all, because it is pointing to the generation that we are not considering, because we are only in the Gen 0 GC. And now we have problem, because this object happened to have a reference to an object that is in generation 0, but we don't have any way of knowing that, because we haven't followed this reference. So we have just lost information about this object and the information that it is still reachable, because there is an older object pointing to it. So as you see, we have problems here. We have problem here with the references between generations, and we could simply lose this object C if we don't solve this problem in any way. How to solve this problem? We need somehow to remember all those older to younger references, because this is the kind of the problem. We don't know that when we are considering only Gen 0, we don't know that they are references from older generation to some objects in Gen 0. So we need to remember those objects, and we need to remember older to younger references. So in particular, we somehow need to remember this reference. And then if we would have this reference somewhere, and this somewhere is in literature called remember set, it would be treated as an additional root. So if this would be a reference stored in this additional root, it will be totally fine. If it would be in this remembered set, the marking would be correct, because it will be starting from the root. We will mark this, we will mark this. This root will be just ignored, but then remember set would be an additional set of roots that we consider. So we will start from here and we will just mark this object because it was visited. So we will be just having this full information about reachable objects. So we need this remembered set somehow managed to keep information about all older to younger references. But as you can imagine, it could maybe, one side note, we don't have this problem with younger to older references because of this decision that we always collect a given generation and all younger ones. So from the opposite direction, there is no problem with that. And this is one of the reasons why it is wise to collect given generation and all younger generations. We don't need to worry about younger to older references, but we still need to cover older to younger. And keeping information about every reference between older to younger object would be something that would introduce super big overhead, obviously, because we can have a lot of such references that will be changing all the time. So such naive approach that we have this remembered set as a list of all references between Gen 1 and 0, for example, doesn't make sense. Instead, runtime tracks this in a less granular information way, and it is covering not a single object as a source of the older to younger reference, but it treats the whole memory regions. and this is based on this card tables mechanism. So we, instead of tracking particular object as a potential as a root from older to younger, we have the card table concept, and for every region covered by a single card we are keeping a bit which will be just saying does we have an object that points to younger generation in this particular region. Every card has this bit set or not, having this information. So as this is seen here, at this point card table consists only of zeros, because there is no an object that it is pointing to the younger generation. But if our code we will be executing, for example, such a code, so we will assign a field of object A that is pointing to some younger object, then it is a place when we need to keep this information. Okay, we have dirted this memory region and we are setting this bit to 1, saying okay, this memory region contains at least one object that contains a reference to younger generation. So as you see, it is kind of compromise, because obviously now we don't have information about particular objects, but about particular memory regions which contains those references. And for doing that we have write barrier, something that we have covered previously in the concurrent mark. Here we also have a write barrier, a code that is being generated by the JIT when such assignment is being done. So in the end, every such assignment of a field will introduce some overhead, because we need to maintain a card table, and this will happen if this object is in the young generation. So there is a condition for that. So every time if you have an old object that you assign one of the fields of it to one of the fields of it, you assign an young object, then you introduce the overhead of the handling the card table, because we need to store this information in the card table, which is setting this bit, for example, to make this region dirty. And then when we are having the mark phase for the young generation, the whole region is treated as a root. So then we scan every object and treat every object inside a region, inside such a region, as a root that may have a reference to a younger generation. So we simply start to follow objects, start to follow outgoing references from every object from within this memory region. And a single card like this covers 256 bytes. So in case of 64-bit runtime, in case of 32 it is half of it. So this region is keeping information about 256 bytes. And if you have an object here which is small and you set this field, you are kind of dirtying all objects inside those 256 bytes, and all those objects inside this region then later on will be treated as a root, as a compromise that we can have between the performance and the overhead of the runtime write barrier. Okay, one question: what if E is not reachable from the roots? Does it mean that the object in Gen 2 makes all objects reachable from it effectively? Gen 2. I'm not sure if I understand the question. So Sergey, if you could rephrase it maybe a little, and I will try to answer Laszlo in the meantime. How much overhead is added because of card table scanning, not because of the write barrier? Whether there is any metric that we can see about overhead from it. So answering the second question, there is no measurement that you could see what is the overhead of that, because I don't know why. I mean, I know the overall approach is that the GCTME doesn't want to expose too much internal data because they may be changed in future. They would rather to provide good automatic tool that handles that instead of us as developers measuring and tuning that. But sometimes we would like to measure and tune, but unfortunately there is not such a measurement. But if you will take a GC stats report in the purview, there is a reason for the condemning particular generations as I described, and as far as I remember, there is the last column which is called internal, and this is the reason which is tracking this one. So the internal reason, the last one provided by the purview, is the reason that is tracking the overhead of handling intra-generational references. If there is too many of them, and if the GC sees that the overall overhead here in terms of quantity of handling these references is big, it is a kind of indication to the GC that maybe those generations are not properly handled. Maybe one of the generation is too big. We have too many intra-generational references. So it will be trying to make and will bump the condemned GC, the condemned generation, trying to help with that. I hope it answers the question. So and the overhead, I will talk about the overhead a little in the next slide, as far as I remember. Carlos, is the card table inspected all together, or when inspecting reference by reference pointing to older gen? Is the card table inspected all together, or when inspecting So the general answer is it is inspected all together. So if a card table at some point in the mark phase, we are simply scanning card tables as potential roots, looking at all dirted pages and scanning memory regions which are dirty. So this is something what is being done there. So I don't know if it answers your question, but in my opinion, it means that it is handled scanned all together, as you said, because we are simply scanning all dirty pages to track the references if we are doing Gen 0 and 1 and are interested in those references that may come from the older generations. So while waiting for the Sergey rephrasing his question, I see you have already asked, if an object in Gen 0 has a link from the object in Gen 2, we cannot collect it in Gen 0 GC because the Gen 2 object is alive. Yes, that's why. So in general, that was something that I mentioned, like if the generation is not collected, we treat all objects as alive there. So if the Gen 2 is not collected, it means we treat all the Gen 2 objects as alive, which means conceptually that we treat all objects reachable from Gen 2 objects as reachable. So they will treat those objects as reachable still, and it will happen because of card tables, because we will be tracking these references with the help of card tables. We will know that this particular Gen 0 object is kept alive from one of the objects in Gen 2. So either we don't Gen 2 GC, we don't do Gen 2 GC because of the card tables, we will know that we cannot collect this particular Gen 0 object. Okay, So this is the thing, and this is the thing, the card table. So one of the optimizations, and this is something that Laszlo was asking, we can get a little of clue that this is a problem, because we will be seeing this internal reason as a reason of condemning generations in the GC stats in purview. And in general, the good rule is, if you would like to avoid it, avoid assigning references to young objects to the old objects. And this is one of the reasons why, for example, functional programming may provide pretty good GC performance, because they don't have this problem, because in the functional languages we have immutable data. So once created, we cannot modify an object, so we cannot assign it, for example, a reference from the newly created object. So immutability would help here, but unfortunately or fortunately, .NET runtime doesn't support immutability at this level, so we need to handle this scenario. Okay, the question from Vitali. So what happens in case object in older generation is lying in dirty card and it is unreachable? So we will discover that in the GC, which will be covering this older generation. So until we don't do that, we will treat this object as live, as we mentioned previously. And if we will be considering this older generation, we will not follow any references from there. So the young object will be just treated as not marked. It will be unreachable, so it will be garbage collected. So we are safe from both sides. Like if we are not doing the older generation GC, we don't care because it will be treated as live, and maybe you have this scenario in mind. So in general, it may be, and I believe we are covering very similar scenario like previously asked. So if you have a Gen 2 object and you don't do full GCs, it means you are not doing anything in Gen 2, but there are some objects in Gen 2 that are referencing objects in Gen 0, then they are kept alive because the information that this reference between Gen 2 and Gen 0 object, this information is still kept in the card table, and it will be used while marking objects, even if we are doing only Gen 0. I hope it answers your question. If not, just give me, maybe you can also ping me on Twitter or somewhere, or you make a comment under the video, even maybe better. Okay, so I said that we have this write barrier hit that's here that sets this bit for a card table, but it is not the whole true. But because, as I said here, even you must imagine that write barrier must be super efficient, because it is something that we are doing pretty often in our code, such an assignment. So setting a single bit is slow in terms of write barrier, because we need to calculate the bit and set the proper bit, and we need to calculate which bit to set. So it is an overhead. And the decision was taken not to set the single bit, but to set the whole byte describing the card table. So we are setting 8 bits in the end. So every such an assignment will set not a single bit, but the whole byte, which means we will make the whole region represented by 8 bits, which is 8 cards, which is 2 kilobytes. That is now invalidated. 2 kilobytes will be made dirty because we have set such a reference to a younger object. This is a compromise between performance and overhead of the write barrier versus the overhead of then traversing from this dirty region, which is now bigger than it could be, because it could be a single card, but it will be 8 cards that are treated as dirty. And we can see such a write barrier code. It is pretty easy to understand if you understand assembly. So this write barrier that we have in the core CLR source code, you can see the very most important line is this assignment. So here we are just assigning this reference, so the code that should be really done, that we are assigning reference between two objects. But then we will see that we are checking whether this target reference is within the ephemeral segment, where those strange values will be patched at runtime by the addresses of the ephemeral region, and we are just checking whether this target, this source reference, the object that we are setting the reference to, will lie inside the ephemeral region, and if it is, we will just set the whole byte as dirty inside the card table. The card table, beginning of the card table address also will be patched at runtime here. And this is the whole thing. Like, we would really like to have this write barrier code very fast, so it should be pretty fast, but still there is this overhead, especially overhead of checking whether this object is within ephemeral segment. So in the end, we are doing this write barrier code, I mean this card invalidation, only if this object is in the ephemeral segment, if it is the young object. If it is not, we don't care, because it would be younger to older reference assignment, and we are only interested in older to younger assignment. So that's why this check whether this object is in the ephemeral segment. Okay, and by slowly ending, we have mentioned about the overhead of scanning card tables, and it could be pretty big, because as you probably felt, you have many of bits to be checked, because we have 256 bytes represented by single bit. So to scan the whole gigabyte of, let's say, Gen 2, it could introduce a lot of overhead. So on top of that, we have the card bundle mechanism, which is just aggregation of card tables. So as far as I remember, every card bundle entry covers 8 card table entries. So it is just a less granular information about what is invalidated. And we are starting from scanning card bundles, and if a card bundle entry is invalidated, it means, okay, in this particular region, we need to deep dive and scan card table for the corresponding card bundle region. So card bundles are helping here in terms of scanning this region, and they are also maintained by write barriers, because we need to invalidate card bundle to say, okay, this region, it has been invalidated. So it is high level view of the same data, but less granular. Additionally, on Windows, the mem-write-watch mechanism was used, which is something that you may remember from the concurrent marking. Okay, and I promised the very last thing, and this is the longest webinar, but the most important one. So just one more thing at the end, the motion, because it is super interesting that we have something like that in the .NET GC, and it is something not well covered in the materials that I have read about the topic. So the motion. I said that we have this pretty nice rule that if an object survives at GC, it is promoted to older generation. And it is true. It sounds good, and it is pretty nice rule. But this ideal story is unfortunately not valid because of pinning. And the pinning might destroy our great idea of the thing that it is always true that we promote to older generation, because we have fragmentation. So imagine that we have this scenario. We are planning or compacting simply, because this is all about compacting in this case. We are compacting such a scenario. We have those multiple objects, and we decided to compact. So we are moving those objects one by one here. We are moving this object, we are moving this object, we are moving this object. Unfortunately, this object is pinned, it cannot be moved, so it is not moved. So with respect to what I've said so far, the generation 1 boundary, assuming it was for example here, will be moved, and now the generation 0 will be starting here, and generation 1 needs to be expanded because we expect that gen 0 object, even if it is pinned, will be promoted to generation 1. Yeah, I hope it does make sense. So we need to expand this generation 1 to contain our pinned object, because we expect it should be promoted to gen 1. But we now have a lot of fragmentation because of that, because we don't have anything more to do. Like, it is the reality that we are having here. If the generation 1 needs to be starting here, now we have some fragmentation in generation 1. So it is pretty problematic, because it is a fragmentation that we would like probably to avoid. We have a lot of mechanism to reuse a fragmentation, but the best thing is just to don't have it. So first approach is just not to have fragmentation at all, and this is when the demotion is introduced. So it is the opposite of promotion. So it is not promoting an object. So in this particular scenario, it is as simple as just moving the generation 1 boundary earlier, ending it before our object, which is a little bit not aligned with this rule, because gen 0 object that was here in generation 0, as you see, stayed in generation 0. It hasn't been promoted. It is demoted, as we call it, because it stayed in the generation 0. And it is also one of the reasons why, because of pinning, generation 0 might be not empty and maybe not 0 in size after compaction because of the pinning. We have some fragmentation now in the gen 0, but we can fit probably allocation context here, so we will be pretty happy. At least we count on that it will be possible. So this is the motion, simply not promoting a pinned object because it would introduce fragmentation. So it is just making more wise decisions about the boundaries of the generations. And that's almost the last slide. We can imagine various scenarios. So it may even happen that an object will be not only not promoted, but also really demoted from the older to younger generation. So if you have this scenario, and we have some objects, some of them are marked, some more of them are not, and if we are compacting, you will see that, okay, we have moved this object, we have moved this object here, so it is nice, and we cannot move this one. And if you remember the mark episode, there is something like extended plug, pinned plug, because we need some place for storing information about it, so about this pinned plug. So in the end, we are not moving the pinned object and one object after it in that scenario, but it doesn't introduce a lot of problem. But because of that, because we have this demotion technique, we are just moving boundaries of generations in the proper places. So gen 2 has been set as here, gen 1 is empty, and gen 0 is just here, which is not empty because we have left this object that has not been moved. We have here a free space, maybe probably for future allocation context. And this is a real demotion, because as you see, we have moved we have demoted an object that was in Gen 1 to an object that now is in Gen 0. So it may happen because of pinning, and more surprisingly, we can even say that it may happen for an object which is not pinned, because this object is pinned, so okay, we can expect it may be demoted, but because we have this extend pinned plug concept, all together with the pinned object, we are also not moving one object after it. So this object, that is totally random object that it just happened to be allocated after our pinned object, is also demoted because it happens it was just after it, so it was demoted as a part of the extend pinned plug. Which is super deep implementation detail, but if you, for example, write a code that expects that object is always promoted if it survives the GC, and you would like, for example, count the number of the GCs based on that, because of the motion, it is not always the case, because as we see, even if an object survives Gen 1, it may happen it will be just demoted to Gen 0. And similar scenario, if we are not able to fit, for example, this plug, it may, if we are able to move this plug, this object will be just staying in Gen 1. This is something very similar to the previously shown. Unfortunately, sometimes we will be not able to fit the whole plug, and will be simply promoting, obviously, pinned plugs as all regular regular plugs. So sometimes it will be not able to use this the motion thing, but it may happen. It really depends on the layout of objects, what will be able to fit inside the previous gaps and what not. So in the end, you can imagine that some pinned plugs will be promoted regularly, some pinned plugs will be demoted. And it really depends what is the actual layout of objects, what is surviving, what are the gaps, what can be filled and what cannot be filled inside those gaps. What needs to be remembered here, that we have a little bit reduced flexibility because we are moving the whole gaps. So if we have this scenario that we have pinned object, one object after it, so we are treating it as a single extended pinned plug. Now we have some plug which consists of many objects, and we need to find a place for the whole plug. We are not splitting this plug into smaller ones to fit it in some gaps, but simply trying to find the place for the whole gap. So it reduces this flexibility a little, which is all about, as you see, the conclusion that pinning introduces a lot of complexity, because it may introduce fragmentation. We need to handle these scenarios, we need to handle the motion, it may introduce different behavior. If we are reusing segments like we saw previously, also we can get a bunch of pinned objects there that will reduce the flexibility of the segments. So in general, pinning like that introduces a lot of overheads. And while the general rule was that you should avoid pinning for a long time, you should avoid a pinning for, you should, maybe in other words, you should pin only for a short amount of time or for long amount of time. That was the rule. Recently, this pinned object heap has been introduced, so now we have the other place for pinned object, and we can expect more and more library code that will be moving to use pinned object heap, and overheads of pinning like that should not happen. It should become less and less severe because we have pinned object heap for that. Okay, it is 2 hours, so it was the longest webinar ever. So if you are still there and are not sleeping, thank you for staying with me so long. I hope you have learned something. Now it is a perfect time for the last round of questions if you have any. So do not hesitate to ask. all this will be recorded, so all answers also will be recorded. And let's look at the questions, whether you have any. Okay, so the first question from Laszlo, maybe question for QA question. When fragmentation gap is too small, it remains garbage and not added to the free list, right? Does it mean that this objects needs to be scanned over and over during the plant phase until not compacted, or is there some optimization? No, there is no optimization for that. So this is one of the another heuristics, dynamic heuristics, that is kept per generation. It simply keeps information what is the amount of such unusable fragmentation, and if it is big enough in terms of bytes, or in case of ratio to the total size, I don't remember now, we treat it as one of the reasons why we should compact simply. If this unusable, so why we don't track the information where those gaps are, we track the information what is the total size introduced by those gaps, and then we can make a decision, okay, it is time to compact because we have too many such gaps. And this is the kind of solution for that, to not have too big overhead of scanning them all again and again. Okay, any more question? If you have any strength, if you are strong enough, you have enough strength for asking after those 2 hours, then I will give you just 1 minute more. In the meantime, I will show you just one thing that I've omitted, and it's maybe worth mentioning, that in this static data there is also a lot of other things, maybe not a lot, but there is those 2 columns are also pretty important. Like for every generation we have these static thresholds, what we concern as a problematic fragmentation, both in the absolute values and in the ratio, like in the percentage of the total size of the generation. So this is the things that will be used by the GC when deciding whether it should compact, or maybe it is still good enough just to sweep. So it is also the static data that is per generation. So I just wanted to point this out. Let's look if we have any more questions. Okay. Carlos. I want to be a multiplier of your knowledge about GC in our company. Yes, you can use those slides. In general, I even haven't marked any source on those slides, but if you all simply mention that those slides are from me or from those webinars, I will be happy. All those slides are available on goodies.netos.org. I believe it is even linked under the description of the video, so you can download PDFs and use those without problem. I will be happy that you are sharing knowledge about the GC. The next question, the magical value part in assembly code for rider is yes, it is updated as the generation, but as the segment, as the ephemeral segment changes. So this is patched at runtime, and if we change the ephemeral segment, it is patched again with new addresses. And note about the voice, your voice is clearer when you speak above or behind. Above, like that. I will make a test about that, to test what's the best approach. Maybe the bass is if I'm too close to the mic. But okay, that's not the GC, so I will try to make some experiments. Okay, okay, that was pretty long one. I'm super happy that I covered that, because it is super hard of the GC, as you see. Next week we will be covering roots internals, also super interesting topic, like what are the stack roots, how they are kept by the GC, how they are interpreted by the GC in something which is called GC info. Super nice deep think about interruptible methods. And also, for example, how statics or thread local statics are represented internally. So we have covered all the things about how the GC works. The only smart part is to have these roots internals, so to cover how the GC is following all the roots, because I only mentioned that they are roots and they are used in mark phase. The next week I will just describe how they are implemented. Okay, so if there are no questions, because I see there are no questions, let's end, as we have over 2 hours. I'm super happy that you stayed with me for those 2 hours. See you next week. As always, slides will be available tomorrow at the goodies.com at the goodies.netos.org. And see you next week then. Have a nice weekend. Sorry, not I'm thinking about weekend already. Have a nice day and have a nice week. See you next week. Bye. And broadcast.